In this clip, we'll consider another resistive-based sensing device. The photoresistor is a component whose resistance is dependent on the light intensity incident on the detector. Here we see an image of a low-cost photoresistor and its electrical symbol. As with the thermistor previously discussed, the symbol indicates that the resistance is dependent on some external parameter, in this case, light intensity. Photoresistors may more properly be thought of as photoconductors, in that they become more conductive as light intensity increases. This is reflected in a negative photoresistivity coefficient. Typical values for common photoresistors are seen here. Under bright light, the device is very conductive with resistances on the order of 10 to maybe 1,000 kiloohms. When dark, the resistance increases significantly to tens of kiloohms or tens of megaohms. The response for this type of device, especially low-cost versions, may be temperature dependent and may have some lag. As such, low-cost photoresistors may not be the best choice if your objective is to develop a highly responsive, accurate measurement of light intensity. This graph provides an indication of the resistance of the photoresistor at various light levels. Note that the range of possible resistances seen, that is, 10 ohms to 10 megaohms, is significantly higher than we saw for the thermistor. We'll discuss the implications of this when we present possible circuits at this clip's end. So how do photoresistors work? They are made of a semiconductor material, such as cadmium sulfide. When the material absorbs light photons, that captured energy moves bound electrons to the conduction band, thereby freeing them and reducing the resistivity of the material. This phenomenon is called photoconductivity. Typically, you'll see a device with a window to let light through. However, not all devices need visible light to work. Some photoresistors are responsive to infrared wavelengths and may be useful for detecting thermally radiating objects. Earlier in this module, we discussed the use of a light sensor to either seek or avoid bright light. Let's consider how we might develop circuits to do these tasks. Our first circuit will consider the case of responding to low light. An example could be a sensor used to track a solar panel, or one to simply turn on a light when it gets too dark. Let's consider the latter, for which we can utilize the same voltage divider setup as we discussed with the thermistor. As we discussed earlier, and we can see from this graph, the photoresistor takes on a wide variety of values. Furthermore, if you don't have a calibrated photodetector, you won't readily know in advance what light intensity you want to turn the light on. As such, you'll want to design initially for a lot of flexibility. One way to do this is by using two potentiometers along with the photoresistor. One potentiometer can have a large range, say 1 megaohm, but very coarse resolution. The other type of potentiometer would have a smaller range, let's say 10 kiloohms, but with much finer resolution. This latter type of potentiometer is called a trim pot. Note that the potentiometer is a 3-terminal device. The resistance between the outer terminals is fixed, and the resistance between the center, called the wiper, and the outer terminals changes depending on the potentiometer setting. So you can use the large and coarse potentiometer to set the approximate threshold for your system, and the trim pot to do the fine-tuning. If you're going to make multiple devices, you would just find the fixed resistors that was close to the sum of the two potentiometers, and then use that in your circuit. So let's take a look at what our circuit might look like. So we'll have two potentiometers. Let's say our coarse potentiometer there, followed by our trim pot, and we'll call that RF for fine potentiometer, connected here to our photoresistor. Okay. Our output voltage of interest will come from this node here, the out, and we'll set the top of this series circuit to, say, 5 volts, and the bottom to minus 5 volts. All right, so this would be applicable to an analog system where our output voltage would be positive or negative depending on the conductivity or the resistance of the photoresistor. Right? So when it was very dark, the photoresistor resistance would be high, and if it was higher than the combination of RC and RF, then the output voltage would be positive. And if it got bright, then the photoresistor resistance would be less than the combination of the two potentiometers, and our output voltage would be negative. And again, we could connect that to an op-amp comparator to give us an analog system, or we could set up the voltages at the top of the series to 5 volts here, or just make this ground, and then take this output and move it to a digital analog converter, and again use a microcontroller to operate the circuit. If our interest was to turn on a device when the environment is too bright, we could simply swap the position of the photoresistor and our potentiometer for producing our Vout voltage. Right? Now, when the light intensity increases, this causes the photoresistor to become more conductive, thereby reducing the resistance. Therefore, more voltage is dropped across the potentiometer, and that causes Vout to become more positive. And again, as with the thermistor, you could take this voltage output and create an analog system with the comparator, or again, just take this output and bring it into a microcontroller. The advantage of developing a microcontroller-based circuit is that you would not need to use a potentiometer necessarily, because you could adjust thresholds in your code. And likewise, you could have the circuit turn on or turn off the output depending on the threshold, and therefore use the same circuit for a sun-seeking or sun-avoiding system by simply altering the code that you write. In our next clip, we'll look at the basics associated with strain gauges. Strain gauge is a sensor used by a variety of disciplines to monitor loads on systems.